The third case is flow in a pipe. Now I need to introduce to you the NS equation in cylinder coordinates. Well, obviously, we will not derive that because the process is tedious and long, and it's pure math. Okay, so first I need to write out the continuity equation, also in cylinder coordinates, right? And with one assumption, either it's one directional or fully developed. Anyway, with the continuity equation plus one assumption, we get another simplified condition, right? So our whole result after that process will be something like this. ddz equals to 0. This means upper stream, lower stream, the same, right? Fully developed. Also, the partial derivative according to theta equals to 0. What does this mean? If I look at the pipe, let's say from right to left, okay, we see something like this. And the theta direction is this direction, right? This rotating direction. So I see the flow property now, let's say. And now I close my eyes and another guy rotates the pipe by an angle, and I open my eyes again. Can I tell the difference? I cannot, right? This means the flow properties don't change with theta. Or you can say it's just symmetry, right? Symmetry. So also we have ur equals to u theta equals to 0. We do not have this kind of velocity, do not have this kind rotating velocity, right? The only thing we can have is the uz. We can only have uz. So this means the flow is just going this way, right? Going in this way. So this means the flow is unidirectional. Now we can write the NS equation in the z direction because we only have uz, right? Here I will, since it's the first time we encounter this, I will write the full form of the NS equation for you. duz dt plus ur duz dr plus u theta over r du theta d theta uz duz dz. The left hand side is very similar to the case in Cartesian coordinates, right? You only need to hit the 1 over r here. But the right hand side is a little different. Well, I wrote a star here. I'm assuming you are familiar with this notion of the generalized pressure. At least this is what I call it. This is a type of notation where I can incorporate the effect of pressure and gravity, both in one term. Okay, so this thing, if written explicitly, it will be something like this, plus rho gz. This is not our emphasis here. Plus mu r 1 over r ddr r duz dr plus r over 1 over r squared du squared d squared uz d theta squared plus d squared uz dz squared. So what can we assume to be 0? Steady. ddr, we don't have ur, right? We don't have u theta. It's fully developed. So the left hand side again is just equal to 0. And here, this term is left, right? dd theta equals to 0. So the second order derivative also is 0. ddz, same reasoning, right? So we're only left with this thing. One over mu dp dz. Well, let's make our life simpler and do not consider gravity in our case, okay? We also see that the pressure can only change with the z direction, so we can write the partial derivative into a full derivative. If we integrate this thing, we need to first multiply both sides by r, right, and integral one time, and then divide both sides by r and integrate a second time. So be careful with the calculations. Anyway, we can get the result as this. For 1 over 4 mu dp dz r squared plus c1 ln r plus c2. Now we need to determine the c1 and c2, right? Can we have c1? I think we cannot, because the pipe is full of fluids. That means the fluid at r equals to 0, that is the fluid in the middle, right, on the middle axis, have a finite velocity. But we know ln 0 does not exist, right? So in order for the velocity at r equals to 0 to exist, c1 has to equal to 0. uz at r equals to 0. This thing must be finite, right? So we cannot have c1. c1 must be 0. Another boundary condition is the no slip condition at the boundary, right? At r equals to capital R. So when r equals to capital R, then uzr should have the same velocity, should be of the same velocity as the velocity of the boundary of the pipe, which will be 0, right? Which will be 0.